Okay, hi everyone. Well, welcome to this third and last session of this book club about Knowledge Graph, the book Knowledge Graph Applied. So this session is recorded and will be published on the KGC networks. So I guess I leave the floor to our speakers today.
Yeah, hello, everybody. Yeah, today I'm going to show you how to build a knowledge graph out of structured data. Last time, Giuseppe showed you how to build from, from ontologies, and last I will show you how to build from unstructured data. So we are kind of a way to know how to build every kind of knowledge graph so far, right? So let me show you this CRISP model. I hope it works. So this is the CRISP model we follow that we presented you already, I think, a couple of times. And if you can see here, the knowledge graph building is kind of a process that is pretty much down the road from the starting point, which is business understanding, right? We want to do the way because we don't want to build, a knowledge graph just for the sake of modeling knowledge and then build an application on top of it and see how it goes, right? In our experience, we found out that it's better to do the opposite, which means to start from the business understanding, understand the business, understand the context, understand the problems that we have, and try to define a solution. Right, and with the solution in mind, we can start to, to think about which data we can use and the preparation that we have to do, and then how to build a knowledge graph on purpose, depending on what we really want to do of the solution that we want to, the goal that we want to achieve, right? And that's what we are going to do now. Consider also that once the model is created, we can come back again with this business understanding, and so getting new data, extending the knowledge graph, right? So this is kind of a starting point of an iterative process. So we are going to build a knowledge graph about microRNAs. So the problem we have to start by asking questions like, why is microRNA interesting? Which kind of problem they're carrying, and how we want to solve this problem. Okay, so very quickly, in a nutshell, these microRNA are related to the cellular gene expression, which can be defined as the ability for the living cell to actually synthesize protein out of genetic material, right? So we should know, let me try to make it a little bigger if I can. Yeah, we should know, understand what we are going here, right? We are in the nucleus, this is DNA, and we are trying to copy a portion of this DNA, a gene, actually to synthesize protein, but DNA is not allowed to leave the nucleus, so the information is copied to this other molecular that is called RNA, right? The RNA can go outside the nucleus, and this is actually the molecule is going to actually synthesize the protein. This process is called transcription. So we see here that the nucleus, the RNA is leaving the nucleus, and it's going to make this ribosomes, and within the ribosome, with the help of other molecular, is going to build the protein. We can see an animation here. You can see right the RNA going to here, and the protein that is starting slowly to be built, right? So that's what happens. And this is called translation. So with transcription and translation, we have, in a nutshell, the ability of cell to generate protein. Okay, so now microRNA are basically RNA in terms of how they are transcribed, but they are too small to actually encode anything useful. They cannot encode anything because they are too small. Look at how long is the messenger RNA and encoding RNA compared to this microRNA. But they are big enough to actually target a very specific part of messenger RNA. And when this happens, right, when they meet a matching RNA, they bind into it. And so basically it cannot fit anymore within a ribosome. So they block the ability to synthesize new protein. So as you can imagine, this microRNA interference is playing a regulatory role in this gene expression, right? The ability to make proteins out of genetic material. And again, as you can imagine, if these microRNA are overexpressed, you may have proteins that are underexpressed, and also the opposite is true. So these microRNA may be related to some disease if they are over or underexpressed. And so there is a medical research that's very interesting about the association between these microRNA and potentially diseases. We have pretty powerful techniques like this microarray analysis that we use to try to understand this type of correlation. Here you see that in this microarray, for every position in the cell, you can put a very specific receptor for genes, for protein, RNA, or whatever, and then you put your culture cells and see the concentration, try to understand if there is some, relationship between, for example, microRNA and a specific disease. But why this is a wonderful tool, it's a very powerful tools that we can use to understand this relationship. You cannot imagine to test every microRNA against every possible disease in the world, right? So what we want to do is to build a knowledge graph about all the information that we have in about this relationship between microRNA disease, and build a link prediction task on top of this knowledge graph to try to understand if a missing link is not there because it's no relationship or because it's not yet discovered. So what we want to do is to build a knowledge graph to feed this machine learning algorithm, to build an intelligence advisor that can give to the researcher information on what to test next, right? So now we have the context, we know what we want to do, and now we can start to actually build a knowledge graph with a purpose, right? So let's have a look on the schema. This is the schema that we have in mind, what we want to build to fit this purpose, right? As you can see, it's very simple because we are basically interested to identify, to discover new relationship of this type. You see, we have the diseases and the microRNA nodes in the middle, and then we have other nodes like normalized diseases. We will see why we need this type of nodes, and other information like, I don't know, the target genes that any specific microRNA is targeting, or the publication referencing this microRNA, or the similarity when it's possible, right, to have it. This is what we try to ingest to build, to give the ground for the next link prediction algorithm to actually do these works. And now we are going to focus on this central part. To ingest this type of relationship, that's actually the one that we are caring about, right? The type of relationship we want to discover. We identify three different data sets to start with. The first one, the main one, is the HMDD, which is, it's capturing exactly what we are interested in, right? Association between diseases and microRNA straight like that. Then we have another data set, it's called DBD-DEMC, which is focused only in human cancer, right? And then we have another smaller data set that does more or less the same thing, carry the same information as HMDD does, but is provides sources for researchers to add new findings. So it's expected to grow into the future. So let's have a look at what we have. Let's have a look on this data set. This is HMDD. It's a TSV file actually, and that's what we get when we open it. You see we have the category, the microRNA, the disease, the publication ID in which this relationship is described, as some description, textual description. We are not going to extract any information from this textual data. We're going just to connect this microRNA with this disease because we know that they are connected, right? Okay, what I usually do before starting to work with the dataset is to run this profile report. It's a library that you can use. I give you an HTML report that can give you some interesting insight about your data, and you can spot easily if there is something that needs your attention, right? So for HMDD, this is a random data set. As you can see here, we have our microRNA connected to prostate neoplasm, for example. Now we have this DBDMC, more or less the same thing. We can open it. We get the microRNA information about the experiment. We have the disease, it's just about cancer. In this case, we have a cancer type, I have a cancer subtype, and we will try to use this one because it's more specific. Then we have other information about the type of experiments, statistical information, the species, if the microRNA is up-regulating or down-regulating in this cancer, and so on. Again, we can run the profiling, and we will see something interesting here. For example, you know that a more representative cancer is breast cancer, then lung, colorectal, and so on. For the cancer subtype, we see that for many entries, we don't have it. So we need to take it into account, like try to go for the more specific if we have it, otherwise go for the less specific. We have to deal with that in the ingestion phase. Again, this is an example of what we get. Basically, same thing for these other data sets, more or less encoding the same information, microRNA, diseases, and some other information about the relationship. So let's have a quick look at the importer. This is how we usually import things. I mean, the code will be available soon, so I will be very, very quick in here. We basically, whenever we have new data sets, we try to create a new class, specialization of this base importer, which we say how to read the record, how to get the data, and how to store it, right? So for example, we can see here that we are doing some basic preprocessing, that we are going to create a node with the disease that we are getting from the data set. And then we create another node that is related to microRNA. We apply a new label on it just to know that this microRNA came through this specific data set. Then we create the relationship, put some description and so on. Yeah, we have it PubMed publication, so we create a reference node and we connect it. That's it, basically. You know, when we can run it, actually, this is what we get from the record that we can try to ingest it. You will see this pretty fast. You know, it's in batches, so those numbers are hundreds of records, and so you can see that that you can be ingested. It's pretty fast. About the DMC, same thing. Basically, the only difference is that we put some more logic on the reading. You know, for example, we select the cancer subtype if we have it, or we fall back to the cancer type if it's not available. Also, what we see before, we do some pre-processing and so on. For the rest, the query is more or less the same. Create a microRNA and connect it to the disease. We can also run it. And as we can see, it should be pretty fast. Yeah, you see, we have much more data in here, but still it's pretty fast. All right. Okay. So since we put this label on top of every microRNA we imported, we can run some analysis about distribution of this RNA. I don't know what it is going down. Probably something on my laptop. Yeah. Anyway, we can continue with the data that we have. Yeah, just a moment, it's finished, so we can run also the other cell. In this cell, we basically are going to run to count how many label we get on every microRNA to see how they are distributed in the 3 data sets that we have, right? So here we go, 2, 1, okay. And that's it. You know, we can see that in this DMC data set, we have much more unique microRNA that was tested, which makes sense because it's about cancer and there is a lot of pressure, you know, about try to understand better how a specific type of cancer works. Here is our main data set. As you can see, we have a huge overlapping. The other one is a little bit small, but still we have overlapping and some uniqueness. This is a good starting point because of what we have in mind to do with this data, right? This link prediction. And we know that we need some kind of overlapping and also some uniqueness. They will give some ground for the machine learning algorithm to try to, you know, to get information that come from these data sets and moving on information coming from these data sets because we have some overlapping. So this is a good starting point, not in general, but because what we have in mind to do with this kind of data, right? Okay, now we have this problem with these diseases. It is an example for this bucket lymphoma, and we have 3 different spelling and 3 different data sets. This is a common problem you have when you ingest from multiple, even structured data set, when you don't have a clear standardized way to identify entities, right? For microRNA, we don't have this problem, because for microRNA, we have standardized, a clear standardized name. For diseases, not true. So we have to understand if it's a big deal or if it's not a big deal, or if we have to do something. In this case, it's a problem because of what we want to do next, right? This will cause confusion in the link prediction algorithm, because the link prediction algorithm will treat these 3 nodes as 3 different diseases, which is not true, right? So we have to do something. We have to disambiguate, to reconcile all these entities. We can do it in many different ways. We can import ontologies and try to match the aliases that we have for every disease, for example. In this case, we try to do something different. We try to use some natural language process technique, like some model, some language model that is trained to, to identify medical entities, like this one. This is size space, right? Which has this entity linker, which is able to identify portion in the text that are medical entities and linked it to some ontology. In this case, in the unified medical language system, which is UMLS, right? Let's see how it works. You see, let's create the model and let's create the entity linker and see how it works when we pass this string. As you can see, it actually identified the part of speech and see that the dependency graph tree is done correctly, but we are not interested in the grammar, you know. But the entity linker is interesting on this. And if we query the entities that was identified, we can see that we have the BERT lymphoma identified as a single entity with this code with an high confidence ratio. If we have a look at what does this code means in the entity linker, we will see BERT lymphoma with the description and all the aliases that are known, right? But really, we don't have to deal with these aliases, because if we go here and we try to a more complex sentence, right? When we have different spelling for BERT lymphoma and other things, yeah, you see these parsing is updated. And if we query now the entities, we see that we have more of them, we have 4 of them. And the first 2 are actually connected to the same ID, but the third one is not. And if we look at the code for this one, you see that we'll get B-cell lymphoma, which is actually B-cell lymphoma, right? They belong from the same category because they are both lymphomas, right? But they are identified as different diseases in this case, and the same diseases in this case. So we have enough information to actually get everything just using this, model to disambiguate and let it to go the heavy lifting, let's say. So we can generate some logic for resolving the disease and create a new importer, which is going to do the same thing as we saw before, but here the data is not get from a data set, but gets from the disease that we already have, right? So if we run it, it will generate this new normalized disease, the one that we see in the schema at the beginning, and will connect to the disease, right? So we can try to evaluate the impact of what we have, of what we have done, right? We can imagine that we may have, since we have created, connecting nodes that connect to different diseases, we can imagine that we have connected some different subgraphs together, right? And we can do this by running some the WCC algorithm with the connected component on GDS directly on Neo4j, right? In order to run this algorithm or any other algorithm in GDS, we have to do this projection, which means that we have to tell the library which part of the graph we are interested in analyzing, and then we can run the analysis. Here we are saying that we want to check the non-normalized version, in which we say that we are interested only in microRNA and diseases and the relevant relationship. And another projection in which we say that we are interested also in normalized disease, and see, compared to the output of the WCC on these two projections, if we merge something. And so we can measure the impact of the reconciliation we just made, right? If we run it, it's super simple. We have just to call the WCC algorithm. It will give you for every node the name of the subgraph it belongs to. We are not interested in these levels. So what we are doing is just to select a subgraph, count how many nodes fall in, and we see what happens. Sadly, in this case, we don't have any information because we started by just a giant component. So we are not merging anything because everything was already fully connected from the beginning, right? And so it is not giving any measure. We could try to run other community detection algorithm that can give you an idea of what happens when we connect these nodes. But rather than try to run random algorithm, graph algorithm, let's try to see what we actually have, right? For example, this is an example of microRNA that are connected to other microRNA to diseases. You see, so this is connected directly to this microRNA because of this disease, and this is connected to this microRNA, not directly because of two diseases, right? So we can define a distance. Let's say two microRNA, the distance in terms of, how many disease you have to cross to go from one microRNA to the other, right? And so the idea is that you see here, for example, we have this Burkitt lymphoma and lymphoma Burkitt. So basically, if we didn't merge them, the distances between these two microRNA should be 2, right? But we know that Burkitt lymphoma, basically this is the same disease. So if we add this information, this distance should be shortened, yeah, right? Shortened, should be 1. So we can do that in GDS. We can run all these distances. And so we can actually perform this measure and see the impact of this, normalization that we did. In order to do that, we have to go again, do a projection. And in this case, we are not going to use label, but we are going to use Cypher query. So basically, we are saying here that for the normal disease distance, this one, we are just interested in microRNA. And we say the two microRNAs are connected if there is a path that is connected the first through this relationship, through the disease, and through the another microRNA, right? We can do the same thing for normalized. And the query is slightly more complex because we need a path going from a microRNA to a normalized diseases, from the same disease to a different microRNA. In this case, we see if we have at least one of those two paths, right? We can tell that these two nodes are connected. And once we have this projection, we can run the all shortest path for both in-memory graphs, right? And this will tell us, if something was changing. And we did that, actually. And those are the results. As you can see, the number of the pairs that were connected by distance 1, directly connected, was increased. While the pair that were connected by distance 2 and 3 and 4 were decreasing, because we see that there is a shift going upwards, right? And this is actually what we did expected, right? And this is something that we have a plot in that sense and a logarithmic plots. And this kind of analysis can give you an idea of the impact of the operation you are doing on the graph using other graph tool. I can give you the quality of the data that you are going to provide to the next layer. And yeah, it's enough. I don't know if you have some question.
Yep, I guess there are a few questions that are, I guess, more related to the NLP processing rather than the graph processing. If you have a few words to say about your experience in evaluating different disambiguation on string matching algorithm.
Yeah,
really...
definitely. If you already have a model like the one that I mentioned before, which is SciSpaCy, which use this UML as something that is very used, right, widely used, right, and not something that you have to train yourself. This is definitely a good way to go, right? To use some the results from training, specialized training, right? It's not necessarily always possible. So when you don't have model that solves your issue, like in this case, we have kind of an entity linker that does exactly what we need, right? Identify different spelling from the same entity, which is this entity linking, the task of the entity linking. If you have it, it's better to go in that way using, NLP techniques rather than try yourself to disambiguate. Even if you have ontologies, which all the aliases, you have to still go for up cases, space, you have to do a lot of tweaking in order to reach the same quality level that you will get out of the box if you already have something trained in that sense, right?
So just to make sure that the SpaceSy model you're using, the SciSpaCy, it has been it's a library specifically built for biomedical.
Yeah, it's a medical.
Okay.
Yeah, it's a model that is trained to, amongst other things, to recognize entity.
Okay.
Medical entities, scientific and specifically medical entities. Yeah.
Oh, thanks. If I may give some context for my experience, I'm working with job ads and online ratings, and it's very, very difficult to deal with that because there is no pre-made model in the job market domain for SpaceSy, and there's lots and lots of typos and really weird typos in online ratings. So that's where we try to approach it by fuzzing the strings and doing some string matching on the one hand, and then weighting it with what we got out of word vectors, and then we moved from word vectors on to word piece vectors just to improve. And in the end, it's a humongous task, and we kind of decided to, in the long run, train our own model from the ground up because we have a really good corpus, but it seemed to us that it is a necessity in the end to have our very own model, even if the training process costs like 2K.
Yeah, there are
AWS
also
resources.
Yeah, there are also products that you can use to help you in a fine training model, right? Using the knowledge that you have, that can be useful, right? They can cut the cost of training a model from ground up, right?
Yeah, this will depend on how good the word piece vectors perform, because we have a very specialized domain of words which is not included in the usual models you can get, and those specialized words we need to catch as well. And this can only be done, to my knowledge, with word piece vectors, or alternatively, if you train the model from the ground up.
But regarding the task of building a knowledge graph, the NLP model is definitely very important, because otherwise you're going to end up, I guess, with messy nodes and everything. Okay, I guess there is no more comments than questions, I think. So we can move on.
Yeah, okay, let me share the screen. Here. Okay, so I would like to share with you the Okay. The outlook of the chapter 5. So unlike Fabio, this is not in the biomedical domain, but this will be in much more understandable domain for general public. So basically, chapter 5 is about, or a first introductory look into how to build knowledge graphs from unstructured data. That means by using natural language processing. The chapter covers like the initial basics, like, explanation why NLP is, indispensable in the knowledge graph domain. Because obviously, like, not everybody is as lucky as having only nice, beautifully structured data, right? Actually, like most of the data that's out there, whether the companies or whether we are talking about the public domain, is unstructured, just raw text. So this chapter is built around using a publicly available news articles dataset and showing how to use Spacey also for tasks like name and entity recognition to build a first knowledge graph, and also how to incorporate knowledge bases such as Wikidata into this knowledge graph, and also some graph-based machine learning based on NLP. Right, so the chapter can be summarized in this schematic image, where at the top left we have various data sources. They can be structured, but of course the focus, as I explained, is on the unstructured data. So we are talking about reports, news articles, books, meeting minutes, things like that, right? We use, and basically there are several steps in this flow chart of a sort, where in each step we basically, deploy one tool set to kind of expand the knowledge graph, make it richer with each of these steps taken. At the beginning, of course, there is the natural language processing, which can mean using the basic NLP outputs such as tokenization, part of speech tagging, lemmatization, dependency parsing, up to the more interesting ones, typically like named entity recognition, right? In the following phase, we can of course integrate also structured data. So, as we all know, this is the huge advantage of the graph databases in general, that they are very flexible. It's possible to adapt them and append data and properties anytime. So here we can use, for example, concept nephthai, Wikidata, which is the most widely used, or the UML, as mentioned by Fabio, in the biomedical domain, to bring in further knowledge, to basically enrich the knowledge extracted by the basic NLP, such as the name and entity recognition. And as a final step, this covered in this chapter is using typically unsupervised machine learning processing on top of that, right? So we can be talking about keyword extraction, similarity analysis, embeddings, topic modeling, relations extraction, all sorts of these tasks, with the final output of a knowledge graph that can be used for various downstream tasks. It can be, used to produce knowledge graph embeddings for machine learning. Can be used to define advanced search, or just, in quotes, visualization, right? And I say just because actually from our experience with many clients, like the knowledge graph in itself, when combined with a powerful visualization tool, can serve as a very big or very significant enabler or eye-opener for the end users, because suddenly they can see it, they can explore the data in previously unthinkable way, right? And it can generate new ideas and new insights, and they can hypothesize and verify the hypothesis. So even just a graph visualization can be, and often is, a very, very useful final output in these kind of projects. All right, so why cannot I switch? Okay. So let's jump into the named entity recognition. As I mentioned, we used here the publicly available BBC News articles dataset from 2006, so it's fairly old, right? It contains business articles, politics, sports, a couple of categories like that. And basically using Spacey NER models out of the box as they are, you can start getting some interesting graphs already. So the red nodes you can see here, these are the documents, these are the individual articles. There is something about Boeing and aviation and Air China. And you can see various entities, right? The green ones, for example, are the locations. So you can see things like US and Taiwan and Sydney and Japan. You can see organizations like Airbus and Boeing and EU World Trade Organization. And some persons, yeah, these are the blue nodes at the bottom right or top right. So we see that already by employing simple NER pipeline, we can get some first interesting connectivity in the graph between or among the documents. Right, but NER on its own is also producing some noise, of course. Like you can see that there's some location entity 7E7, right? And also there is a lot of ambiguity, right? Because you can imagine, like here is example of the EU and European Union. Like we know that this is the same thing, but just relying on NER, you see them as two different entities. So the graph could use a little bit tweaking after the NER step, obviously. And the similar is true for organization, right? So here we know that there is Airbus, there is WTO, there is Boeing, but what are they? How are they related? And what is their domain, right? So this is the phase where it's very useful to actually incorporate some external knowledge, to do some knowledge enrichment, and be it using some external publicly available knowledge bases like Wikidata, which would be used in this chapter to enrich the organization nodes, right, by looking at the industries of the organization, the subsidiaries, the ownership structure, the memberships, right? As just as an example, what can be done. Or, of course, some organizations also have some internal knowledge bases. They are not publicly available and that they would like and they can incorporate in the knowledge graph, right? So you can combine the unstructured and structured data. And of course, like here is a simple article as an example, like it's about Elon Musk and Apple and HomePods, right? So you can see all these entities, the person Elon Musk and some time like last year or date February 9th, 2018, right? Extracted from the article. And as a next step, you can find out that Elon Musk is a founder of SpaceX or of Tesla, right? Or that Amazon produced an Echo device and Apple produced a HomePod, right? So this basically unlocks more opportunities to increase the connectivity and insights generation from the graph, because suddenly you can connect articles which just mention Amazon with articles that mention just their Echo device without specifically mentioning Amazon, for example, or Elon Musk and his companies, right? But let's step now from the NER a little bit back again to the NLP domain, right? And here I stated NLP is a graph. And what I mean is that when you look at the output of basically every generic NLP pipeline, you can get something like this, right? So here's an example sentence, like Jane Austen, the Victorian era writer, works nowadays for Google, right? When it's analyzed by the NLP pipeline, it's split into individual tokens. The tokens are classified, for example, by part of speech tagging and named entity recognition, right? And you can have also grammatical relations like these universal dependencies, like Jane and Austen, they form a compound, and there is a subject relationship between the works and Jane Austen, and so on and so on, right? And you can see already on the first look that this is basically a graph. We see nodes, relationships, and properties on both nodes and the relationships, right? Of course, the question is this somehow useful in practical way? And we believe it is. And that's what we show also in this chapter on the example of topic modeling approach using the NLP, right? And graph algorithms. So basically, at the beginning, we have a news article. We run it through the NLP pipeline. We can use the output of the NLP analysis that we just saw for defining a keyword extraction algorithm unsupervised, such as text rank, right? So you don't need any super fancy machine learning. You can like achieve a lot already with basic NLP analysis plus plus using PageRank on top of. We will get to that. So you can extract keywords representing semantically most meaningful words and phrases describing the original article. And this alone, the keyword extraction, can be fairly useful to generate some initial insights and some more value in the graph. But besides that, you can perhaps use the keywords to define document similarities, right? Because the many documents will share the same keywords. So, for example, you can use Jacquard similarity to calculate how much similar the two documents are, and then perhaps Louvain community detection to identify communities with documents. So basically, sort of clusters of topics of documents that discuss similar things. And as a final step to get a real topic modeling approach is to assign to these clusters some descriptions, right? Something that some word or collection of keywords in this case that describes what the cluster is about. For the keyword extraction, and back to the thought that NLP is a graph, this is one way how we can do it, right? This is based on the TextRank paper. You might know it. Spacey also has implementation of TextRank since a few years ago. And basically what it does is that, if we take here as an example of an article, brewers' profits lose their face, then, the article started like Heineken and Carlsberg, two of the world's largest brewers, have reported falling profits, and so on, right? So you basically can turn the article into a graph of tokens. Like we see Heineken connected to Carlsberg, which is a large brewer. They reported profit drops in beer sales, and etc., right? And so you can build, using the NLP and the graph database, this token co-occurrence graph, normalize it accordingly, and perhaps use PageRank centrality for identifying the important tokens in this graph, and then use some post-processing to actually be able to extract also key phrases, not just keywords, right? So at the end, at the output of this, you have keywords for this specific article, such as falling profits, 10 billion euros, increased marketing costs, foreign sales, Western Europe, and so on, right? And how this can be used is, for example, for generating or identifying similar documents regarding the topics discussed in them. So like I mentioned, you can use, for example, these keywords plus the Jacquard similarity, that is to analyze for each pair of documents the amount of shared keywords versus the size of the union of the keyword sets for both of the documents, right? Fairly simple approach, but you can already get like documents that, here is about Renault and about Brazil and Lufthansa, and I think these are some low-cost airlines and so on. And you can see the keywords through which they relate to the original article, brewers' profits lose their face. And it's all about sales and net profits and Western Europe and costs and so on, right? So fairly interesting results with very simple, inexpensive approach. And to turn it into the final step, that is the topic modeling, then what we can do is to use the keywords, document similarities, to run, for example, community detection algorithm such as Louvain, right? This basically clusters the documents based on the modularity scores. And well, final step is to basically find some interpretation of these clusters, of these topics, right? So that basically means to assign them meaningful set of keywords. So in the example of the article that I mentioned, the brewers' profits lose their face, this article was assigned to the cluster, which was found to be represented mostly by these keywords, such as General Motors, Fiat, net income, strong sales, Western Europe, market sales, net profits, sales growth, and similar, right? So yeah, the final knowledge graph schema at the end of the chapter looks like this. Like we have the document in the very center. This is the news article. We have entities connected to it. Like here we use the convention that we name the relationships like mentions underscore location, date, organization, person, and so on. From the knowledge enrichment, we added some additional relationships and nodes also to the organizations. So we have the subsidiaries and memberships and ownership structure, or the industry where the organizations appear. And at the end, we have the keywords which form the communities. So the topics basically extracted by unsupervised way, and the documents are belonging or assigned to these topics. Right. So, like I mentioned, this chapter is intended as an introduction into the unstructured data processing. There are other chapters in the making. Specifically, you know, as you can imagine, typically you will need more customization, especially in very specific domains. So we are looking into chapters about customization in ER models, or entity relation extraction, or specifically named entity disambiguation, as was already discussed in the beginning of this session. So yeah, this is chapter 5. I don't know if there are any questions, comments.
Thanks. So there have been some discussion in the chat going on. Starting from, do you have any experience with authoring a UI and a CMS requirement for that knowledge graph to feed a website, for example?
Oh, okay. Interesting. I'm not sure. Maybe Alessandro has a bit more idea about this specific question.
Well, no, I think that this was never happening to us. To be honest, in the world of CMS, we never worked. You know, what we did was the opposite instead, using the content generated maybe in some CMS, you know, to extract some knowledge. But for authoring, this is the opposite, you know, and this was not our. I mean, at least none of our customers asked us for doing that. You know, as I said, the opposite, definitely yes, but yeah, it's hard for us to use this. I mean, what we did in the past as a sort of connection is to use these topics recognition or this classification to sort of organize the documents, you know, and these could empower search capabilities in our case, we were empowering the search capabilities in a e-commerce domain, in a commerce website, you know, in this case. So it was not a real authoring; it was more about improving the search capabilities of these platforms. But it was not a CMS; it was let's say a site like Amazon, just to give you an idea, in which you have the multiple type of let's say products that have to be sold.
And thanks for that answer. And apart from what you used as findings from the NLP, did you manage to harmonize that with already existing metadata?
What do you mean for metadata? Like ontologies or?
Not really, like what they just use the e-commerce website, or you told me that they should have some classifications or stuff. They already should be putting products in categories. Did you use?
We were using what was already available there. You know, really the classification, the internal classification was meant to just you know, aggregate documents or aggregate products to offer the classical, like people were interested also in, for example, you know, or this kind of classification, but not really did to a standard classification mechanism that was provided as a part of the let's say the input.
Okay, thank you.
I have a similar. Oh, sorry. Go ahead, Matthias.
No, I was going to give you the chat, but I want to make sure we answer all the questions in the chat afterwards. So
Yeah. But I just wanted to follow up, sort of related to that, Alessandro. I'm curious if, because people like Theodora and I are taking an interest in this stuff, and there's going to be an ongoing conversation about, because we're all concerned with structuring data, assigning, we're doing the other side of this, ascribing semantic meaning to the content we create. Do you see like a place or a mechanism or a way that we can get that conversation started and interact more with folks like y'all?
Well, definitely, I think that this is an interesting topic for us in general terms, and we are constantly looking for, let's say, for ideas and applications where the knowledge graphs could play a key role. I think that you have all our contacts, and we are available even in the Knowledge Graph Conference Slack channel. So you can reach out to one of us, and we will be more than happy to set up a call, and we can go more in detail in the options available, for which we can just start some new ideas or to leverage some opportunities here and there.
Perfect. Thank you.
You're welcome.
So we have another question about how to validate or evaluate the generating model. So I'm not sure here, and Sarah, you can specify if the model are the machine learning models or the actual knowledge graph. But
Yeah, I was referring to the machine learning, those models, understanding, are they working as you anticipate them to work, and sort of just the process of looking at that.
That's always useful in the knowledge graph to kind of implement a feedback loop, right? Be it for the NER models, for the interrelation extraction models, right? This can be potentially a very complex task. And when you look at the literature, like the precision and recall of the relation extraction models is not always super large, right? So there is always a certain level of contamination in the knowledge graph. And, the thing is that with the knowledge graph, it's fairly easy or simplified to basically implement a feedback loop. So basically people can just not see the relation, but we can also implement or put there some metadata that allow us to identify where the relation comes from, show that to the people, and they can verify very quickly for themselves whether it's a valid one or not, and do some corrective action, right? And when you let the analysts work like that, use the graph, sometimes they notice things here and there, then they start giving feedback, and you are collecting this feedback. So basically, you can do the whole circle. So at some point you can say, okay, I collected like enough feedback. I can use this feedback to update the training data set, retrain the models, redeploy it, and produce a new knowledge graph, right? Or similarly, when we're talking about data drift, right? So basically some underlying structural change in the data you are ingesting. So I don't know, for example, you are ingesting historical documents, you train NER models for that, and then you start adding a decade later, and then 2 decades later, and so on. And eventually you might notice that the models start to deteriorate. Well, you might not notice it unless you implement this feedback loop, right? So this is super useful also for this purpose, because it allows you to monitor like how these reports of failures by the analysts using the graph evolve over time, and you can take again some timely corrective action when needed, right? Of course, if your question was more related to the unsupervised part of this presentation, then of course, yeah, this is potentially like complex, because it's not a really classifier. Like for example, the topic modeling, right? It's more a modeling than the classifier. So you don't have a predefined set of clusters, predefined set of topics, and just classifying documents into them. You try to identify something autonomously, right? Find what are your topics and how many of them. Like you have no idea, right? It's just a collection of the documents in the very beginning. So yeah, definitely this is a very, very interesting question, and there is a lot of iterations, typically fine-tuning the parameters, evaluating the results, but in the end, yeah, some human interaction is needed to help with this task. And yeah.
I hope it does answer your question, Sarah.
Yes, that's helpful. Thank you. I know it's not an easy question to answer, but thanks.
I guess we have a few minutes for a last one. Marc-Antoine is getting the impression that the spaCy syntactic structure is not exploited fully. So he's asking if there is any work in that direction.
Not sure what exactly is meant.
I was referring to one of the last slides you showed, and a lot of the links were, oh, this refers to that, this refers to that. And so there was a lot of analysis of reference, whereas it would be in theory possible from the spaCy syntactic graph to go further and to detect increase, decrease kinds of relations. And I found the relation types to be quite limited. Is that an impression? Is that something you're exploring? Like looking
absolutely.
inside the, yes.
So I think you are more referring to the entity relation extraction, right?
Well, more the relation extraction.
Yeah. So yeah, absolutely. I think this is definitely coming in one of the next chapters, right? So here we wanted to, give an initial feeling of how the unstructured data can be used, just using out-of-the-box tools that are out there, plus some, basic analytics like graph algorithms and so on. So yeah, it's coming.
Excellent, thank you. That's looking forward to the next sections of the book. Then
that's good. Glad to hear that.
I think we have one last comment from Quentin.
Yes, it's more like a general remark, but I mean, we work a lot with organizations that are nowhere near implementing any NLP. So it would maybe be interesting to see for every maturity level of the organization, no experience with knowledge graphs and NLP, how do it go about like implementing like this solution? Because from your presentation, it's already quite advanced, I have a feeling, and you need some NLP experts in your organization to start implementing. So what is the maturity level that you assume for going on and building a knowledge base for organization in this setting? And are there also some, if you have no experience, no prior experience, would you then advise a different approach to start building a knowledge base? Or are there some maturity levels that you see there working with your clients?
Well, in the book, we try to be open to all levels, right? So that's why we have these chapters that, for example, utilize the out-of-the-box models, as well as we will have the more advanced chapters that basically explain the customization process and the whole iteration of building data, training a model, evaluating it, figuring out it's not good enough, training a new batch of data, and so on, right? So yeah, definitely we try to be like reasonable in terms of expectations, but in the end also we want to serve some people and readers who have some knowledge and want to a bit consolidate it and perhaps expand it, right? And I don't know, it sounded maybe like you are asking also about the business model or how to say it, like what we do at Graphiverse. So of course, like we have experience with both using both clients that have literally zero data scientists on the team, and like we help them to build knowledge graph because we have a data scientist team within Graphiverse. Plus we have the product that helps to build and visualize and analyze the knowledge graphs, right? And we also have experience with clients that do have data science teams and just want to brainstorm a bit here and there and want some help and things like that. So we do both approaches.
Okay. Oh.
Nice. Yeah, maybe if I can comment on that, it would be nice to have some sort of decision tree, because sometimes we've seen knowledge graph projects being blown off because the NLP was a little bit too hard, or would require a little bit too much upfront investments because they had so specific terminology or glossary that was really required some manual training. And so having like a view or like an easy to approach question or decision tree that you can ask in your organization would actually be nice. I'm not sure if that's something you've been working on in this book or if it's on the roadmap or.
Yeah, interesting. You can give it some thought, right? I don't think it's currently included in any chapters, but yeah, Alessandro, go ahead.
I think that these will be addressed in the next chapter that you are working on, because the main concern that Quinten has is about the customizability of the models, the NLP models for specific domains. It is a problem that we constantly have. Let's say that in reality, in our business, let's say not in the book, but in the book will be mentioned that we are partnering with a company called UBI that actually aims at, let's say, building a custom language models, in which you can have your expert that will annotate a few documents, and they have a quite nice interface and machine learning models to help you to make this process as smooth as possible. And then we build custom models. This will be mentioned also in the book as one of the approaches that you can have to build your own knowledge with your own language model with less experience than what you think. Because they are driving you through the entire process. Then in theory, what you have to do is just download the model and use instead of what you're using, for example, as a standard model. So it is I don't want to say straightforward, but it doesn't require you to have a big knowledge. Let me say that in general, we are graph expert. We are not an NLP expert, So we are, of course, supporting our customers, as much as we can, but we are not, for example, building a new algorithm for language models, So we are leveraging what is available out there. And to be honest, with a discrete success, I would say, of course, we are not considering ourselves as super experts, but we are achieving our goals. We always try to find the best way with less effort in the NLP space for achieving a certain level of precision and recall sometimes. And in this case, in which we have specific needs in terms of domains, UBI is filling the gap, let's say, of the availability of public let's say, domains that you can easily find on Hugging Face. Whenever this is not the case, we have UBI that can support us. So that's the way in which we are moving. But again, if you have some further questions, really for you or for anybody else, feel free to reach out to us. The purpose of this book club was to generate questions and try to provide as many answers as we can. But of course, if there are more, we will be more than happy to provide more details, at any level, at the level of the book or the level of what we are doing for, as GraphAware for supporting our customers.
Thank you. I'm going to stop the recording here. I can